All right, guys, we are going to talk through population dynamics today. And I will dive right in. So, at the beginning of the semester, we talked a little bit about the definition of a population, but let's go back to that. So, a population is a group of individuals, the same species, living in the same general geographic area. All populations undergo various distinct phases of a life cycle of that population. So we usually see population growth that occurs when resources are abundant. Often the number of individuals that can exploit them causes the population to increase. Reproduction can be rapid. Death rates may be low in that case. And we see a net increase in population size. Sometimes we see populations stabilize after a time of growth, and often that stable period is the longest period in the phase of a population's life cycle. But that's often followed by a population crash. Once the population starts to outstrip its resources, then we can often see a decline in the population. And sometimes that decline is dramatic. So, of course, population size is affected by food supply, sufficient home sites, the ability to successfully reproduce, and it has to be able to mitigate for the effects of dispersal, immigration, emigration, climate, predation, disease, and parasites that can also affect the population size. We know populations grow with birth and immigration, and populations decrease with death and emigration. So we'll talk a little bit more about the types of factors that affect populations and those that are density dependent and density independent. It's good to get our heads around this idea of reproductive potential within a population. So the reproductive potential or the contribution to the next generation, the maximum number of young that a population can produce under ideal conditions during a particular time. So in a healthy population, the birth rate will most likely exceed, if not outstrip, the death rate. Most populations will level off after it reaches a certain size. So the point at which the population levels off can vary within the species. Generally, a natural population will continue to show fluctuations around a leveling off period. And we refer to that time of leveling off as the population having reached the carrying capacity. Individuals within a population, of course, affect the reproductive potential in several ways. So an individual can have more offspring, they can have a longer reproductive lifetime, and they can reproduce earlier. So those factors, age of reproduction, fecundity, which is the number of young produced each year, the survival of those young, and the survival of the reproducing individual all contribute to that total population reproductive output. So it's interesting to think through some of these items that affect reproductive potential. And so a couple of these notes I have today, I've actually added. These are not things your book covered on populations, but I think they're important. So in thinking about reproductive potential, it's interesting to look at some of the extremes in in the avian world, we look at several factors that I just mentioned: survival before breeding, age of reproduction, fecundity, and the adult mortality rate. And you can compare those two for albatross. Wandering albatross start breeding at 8 to 11 years of age and produce one chick every 2 years, but for up to 50 years. In contrast, we see ducks breeding much earlier and producing more young per year, but living a shorter amount of time. So we can use these statistics really to project the life expectancies and family sizes that individuals face. We can look at these life tables and project out population growth. And we can also use these to better understand the times in the life cycle that are most sensitive to change, and we can target those to help maintain healthy, stable populations. We've actually seen this with waterfowl management in the past. And this is a similar concept here, where we look at the area under the curve in the graph and compare the reproductive output of sparrows and penguins. And what we see is that the short-lived sparrow produces young every year, but lives a much shorter time. And these two strategies actually result in roughly the same reproductive output over a lifetime. I want to talk a little bit about population growth curves that we see in the natural world. So a pattern where the population doubles in a constant amount of time, we call the a J-shaped curve or exponential growth curve. So in the graph, you can see that the curve on the left does look like the letter J, and the population is doubling at a constant rate over a constant amount of time. So nearly all populations will tend to grow exponentially as long as there are resources available. Most populations have the potential to expand at this rate, since reproduction is really a multiplicative process. Two of the most basic factors that affect the rate of population growth are, of course, the birth rate and the death rate. So we'll talk a little bit about R. R is the growth rate of a population and the difference between the average birth rate and the average death rate. And when we look at population dynamics and read on population growth, you'll often see that referenced in formulas. When the birth rate is larger, and as large as it can be, and the death rate is at a minimum, we call that the R max, and that's the intrinsic rate of natural increase, the highest rate that we expect to see in that population. On the contrast, the logistic growth curve on the right shows what happens when a limiting factor is imposed on a population. And we call that limiting factor the carrying capacity. We'll talk a little more about that. So often after an initial period of exponential growth, a population encounters a limiting factor that can cause the exponential growth to stop. The population enters a slower growth phase, and often that growth levels off or stabilizes at a fairly constant population size, with some range and fluctuation around that carrying capacity. So in the graph, you can see the population fluctuating around the carrying capacity. We refer to carrying capacity as K. And the carrying capacity definition is the maximum number of individuals that the resources in a given area can support for an extended period of time. The most unfavorable time of year is the most critical to reproductive success. And we see this usually being affected by availability of food and shelter. Some other examples of populations fluctuating around the carrying capacity, natural populations from your book. So what actually limits populations? Let's talk about density independent and density dependent factors. So the environment's the ultimate cause of population stabilization. Two categories of factors are commonly used: physical environment and biological environment. There are three subdivisions of the biological environment, which are competition, predation, and symbiosis. The physical environment includes food, shelter, water supply, space availability. For plants, that would include light and soil. One of the factors may severely limit a population. So even if the others are not as constrained, the law of minimum states that population growth is limited by the resource in the shortest supply. So we know some factors are density dependent. That is, the effects varies according to the population density. Other factors are density independent, and affect population size regardless of the number of individuals in the population. So density independent factors like rainfall, flooding, drought, temperature play a critical role in limiting the population. A fire or a volcanic eruption is going to alter a population size, whether it's small or large. Freeze that kills the buds of hardwood trees, oaks and hickories, and other mass-bearing trees might create hardship for the animals the following summer, fall, or winter. And of course, rainfall or the lack thereof can drastically affect reproductive success of amphibians and waterfowl, despite the number of individuals present. And then density dependent factors are those whose effects will really vary directly depending on the density of the population. So, for example, population density increases. We know that home sites and food may become more scarce. As the rate of individual contacts increase, interspecific aggression can increase. Females may stop breeding. The rate at which nestling young are killed by their own parents can increase, and even the rate at which juveniles are forced to disperse from the population can be greater. We see parasites and disease increasing as populations increase as well. So in some areas of the world, increasing wildlife populations are, of course, creating problems, especially when we see populations that have been introduced to areas and don't have the natural constraints on those populations and on those invasive species. So your book actually talks about an interesting goal in New Zealand. So Australia and New Zealand have rampant invasive populations, for instance, of rabbits, and the book talks at length about the control measures that they're using to try to control rabbit populations. Interestingly, New Zealand has set a goal for eradicating all non-native predators, including rats, possums, and feral cats by 2050. The Prime Minister there says those animals kill up to 25 million native birds each year, and getting rid of them is likely to be one of the most ambitious conservation projects that ever attempted anywhere. So it'll be interesting to follow that. Predators often limit their prey populations, and in rare cases would drive them to extinction. But of course, prey in turn can limit their predators. So there have been several interesting studies that look at predator-prey dynamics. This example from the book shows the population cycles of snowshoe hares and the Canadian lynx over a 9-year period. And you can see that increases and decreases in the hare population are followed by increases and decreases in the lynx population as well. Populations of some species like lemmings and voles show rhythmic fluctuations. Populations increase for several years and then fall off dramatically. And due to the intricacy of food webs, like in this picture, anything affecting one species is likely to affect several others. So prey abundance will be reflected in increasing numbers of predators, and this type of cyclic pattern of communities is common. The book talks about eruptions of species. That's when enormous numbers of animals sometimes occur in a given area for a brief period of time because certain environmental or climatic conditions have allowed for it. So we may see abnormally high numbers of a given species when there's a combination of mild winters, abundant food supply, or removal of predators from the environment. We talked early in the semester about life strategies, but we'll revisit this because of its relevance to populations. So let's talk quickly again through R strategist and K strategist. So R strategists are species that are well adapted to have high values of the R max that we talked about already. So in general, they are small, short-lived species. They're able to take advantage of new opportunities and changing conditions in an environment more efficiently than sort of the low R values in K species. They tend to live in variable climates, sometimes in unpredictable habitats. Mortality tends to be caused by density independent factors, weather, and catastrophic events. Population size fluctuates over time. They may have limited competition, short lifespans, rapid development, and early reproduction. K strategists have adaptations that increase their ability to maintain populations as close to carrying capacity as possible. So K strategists tend to have long lives, reproduce late in life, produce just a few large offspring, and provide extended parental care. They tend to live in more predictable climates and habitats. Mortality is caused by density dependent factors. Population size is constrained over time. We often see heavy competition, longer lifespans, slow development, and later reproduction in these guys. And of course, we can't talk about animal populations without thinking about human impacts on those. So of course, human populations themselves have continued to increase due to technology that's really disrupted natural populations as well. So destabilization of populations leads to a couple of possible outcomes: population growth as previous limits are removed, and population decline as new limits are imposed. And we can look at lots of vertebrate populations and understand how humans are impacting that population growth. And our own population growth over time is interesting to contemplate as well. So human population growth over the past 10,000 years is captured in this figure. Note the effects of worldwide disease like the Black Death in the 1400s and technological advances that really had huge impacts on our population growth rate. A few notes and review questions from the book, and I will stop the recording now.